Section 5.5 is on the graphs of relations and functions. So we're first going to start out talking a little bit about discrete versus continuous data. Continuous data basically is data that when you plot the points on your graph, you would connect the points. And continuous data would be basically data for which all real numbers are possible. For example, if you're talking about a graph that had distance and time, you might only plot certain times, the distance, like time 0, what the distance was, time 10 minutes, what the distance was, time 20 minutes, what the distance was. But you would connect those points with a line because all the times and distances between those points were reached. So that would be an example of continuous data. Discrete data, on the other hand, is usually when you only have a series of points on your graph that would not be connected because not all the values in between those points are possible. An example where that would occur would when you're talking about things representing the number of items or the number of tickets sold or the number of cars sold. In that case, you can't have half items or half or quarter items or 1.5 or 2.5, so you'd only have whole numbers. So therefore, you would not connect the points. So kind of a quick way to help you remember it is think discrete goes with dots and continuous goes with connect. Just a little, D for dots and C for connect. Okay, so just a little thing to help you remember it. Some people get continuous mixed up and think that continuous means, the pattern continues, but you have to think continuous means connect. Discrete means dots. Okay, so we're going to look at some examples here of some relations and decide whether or not they're discrete or continuous data. So the first one shows a straight line that has all points connected, so that would be continuous. The second one just has a series of points. They're not connected, so that would be discrete data. The next one shows a graph with a line connecting all the points, so that would be continuous data. The next one as well, all the points are connected with a solid line here, so that would be continuous data. This one here would be again a series of dots, so discrete data. This one here, all the points are connected with a solid line, so that would be continuous data. And same thing with G, is a continuous graph, continuous data used. The next one as well would be continuous. This is a solid line connecting all the points. The next one is a little bit tricky because there's parts of the graph have solid lines there, but when you look at it, in terms of the y-coordinates, not all the y-coordinates are possible. So there's only whole numbers used for the y-coordinates. So if one of your pieces of data is whole numbers, then you wouldn't be able to have continuous. You wouldn't have a line that's connecting all those points. There are gaps there. So this would be discrete. Okay. Our next example uses some graphs there, and you're asked to state the domain and range for each relation, shown using set notation. So the first equation, or first graph, has basically your x's that get used start at -4, and all the x's above -4 on the x-axis would have a point on that graph. The graph keeps going further and further. The arrow indicates that it's going to continue going to the right. So all the x's from -4 above -4, not including -4 because of that open circle there, would have a representation point on that graph. So we start off with set notation, and we start off with our basic statement first. So the x's that get used are greater than -4. And then we would put our fancy stuff for the set notation. So that would be the set of all, the curly bracket, the set of all x is such that x is bigger than -4. And this is continuous data, and normally with continuous data, we would have x as a real number. The range starts at that point as well on the x-axis there. Negative 4, 0 are the coordinates of that point. And all points that are on that graph have y values or y coordinates that are above 0. That graph continues to get higher as it's going to the right. So it would be y's that are greater than 0. And again, you put your fancy stuff, the curly brackets, y such that, and continuous data normally would be using y as a real number. The next graph, if you look at the x's, this graph has arrows on the ends. The graph is getting wider on both sides, so it's going out, out, out further. If you go up, it's going out further, out further. So no matter what x you pick on the x-axis, you will be able to find a point on that graph that has that coordinate as its x-coordinate. So no matter 2, like 2, 3, 4, 5, all those, 1, 0, negative 1 has a point, everything, no matter what you pick. So that would be x's. All numbers are represented on that graph. And then to set notation, you have your curly bracket, x such that. And you don't need to repeat x as a real again. That is your statement, so you just end it off with curly brackets. And the range for this particular relation, if you look on the y-axis, the lowest y that has a point corresponding to it on that graph is this point right here, and the y-coordinate would be 0. Everything else, that graph keeps getting higher and higher and higher, so every other point on that graph has y-coordinate that's bigger than 0. And because 2, 0 is a point on that graph, y can be equal to 0 as well. So we'd have y greater than or equal to 0 for our statement, and then we put the curly brackets, y such that, and comma, y is a real number because it is continuous data. The last example there is just a series of points, and there's only a few of them there to list, so the easiest thing to do there would be to say that x is a member of one of these numbers, 1, 2, or 3. And that would be discrete data. We just list off the numbers. And for the y's, it'd be y. The y's that get used on those points are 0, and 1, and 2, and 3. So if there's a series of points and there's only a small number of points, you can list off the data like that. Sometimes, if there's a lot of points and the pattern keeps going, it means it's impossible to list all the points, so that you just put dot, dot, dot. Examine the matchstick pattern for number 3 and C. Complete the table below to determine the number of matchsticks required. So if we look at this pattern here, the first triangle pattern made of matchsticks has 3 matchsticks used to make the triangle. 1, 2, 3. And then if you look at the next pattern, they basically only have to add on. You got the 3 that you started with, 1, 2, 3, but then they add on an extra 2 more, so that will be 5 matchsticks in that pattern. And then you've got the 5 that you started with from the previous triangle, and you add on an extra 2 more, so that would be 7 for the third. And you can see that basically adding on an extra triangle means you're going to have to add on 2 extra matchsticks to the pattern, so that will be going up by 2s. To be 9, 11, and so on. So if we sketch this pattern on the graph, we would have our x-axis would represent usually our independent variable, which in this case would be the number of triangles, and then the dependent variable would be the number of matchsticks. Depends on how many triangles are in your pattern. So that would be the dependent variable number of matchsticks, and that would go on the vertical axis. So we'll just label the vertical axis with an M and the horizontal axis with an N, and just to space it out a little bit, do use 2 blocks, represent 1 unit on the horizontal axis. And we'll use, now we got to go a little higher on the y-axis, the vertical axis, so we'll just probably go 2, that's supposed to be 4, that's supposed to be matching up right there, sorry, 2, 4, 6, 8, 10, and 12. So 1 goes with 3, which would be right here. 2 goes with 5, which would be right here. 3 goes with 7, which will be right here. And 4 goes with 9, which will be right here. And 5 goes with 11. Is the data discrete or continuous? Question C asks, and we would say discrete here because you can only have whole numbers for the number of triangles and the number of matchsticks. Okay, so the next question is to identify the independent variable and the dependent variable, which we've already done. We'll write it down now. So the dependent variable we said was the number of matchsticks because the number of matchsticks depended on the number of triangles that we had. So the dependent would be the number of matchsticks, M, and the independent would be the number of the triangles in the pattern. Does the graph represent a function? Well, if you look at this, no matter what graph, whatever point you look at, there's no two order pairs with the same x coordinate. And this graph, this pattern, as you can see, when you have one triangle, you're only going to have 3 matchsticks. There's not 2 possible y values that will go with that. The same thing with if you have the number of triangles as 2, there's only one answer that's going to go with the number of triangles as 2. So you'll never have 2 ordered pairs with the same first elements. So the answer to that question will be yes. Okay, this next example is about a candle which is lit and left slowly to burn, and the height of the candle is monitored and recorded, and the data is organized in the table given there. So you're asked to sketch the graph on the grid provided, so we first need to label our axis, and in this case the candle height depends on the time. So the candle height would be our label for the vertical axis, or height would be our dependent variable in centimeters, and time would be our independent variable in hours. So we'll just label 1, 2, 3, 4, 5. So every second block is labeled. And then on the vertical axis, we need to go up as high as 18. So we'll probably do every block will be 2. So this will be 4, 8, 12, 16, and 20, just so they can fit them all in. So the first time at 1 hour, the height is 18. So that would be there, halfway between 16 and 20. And then 2 would go with 16 at 2 hours, it goes to 16. At 3 hours, it goes to 14. 4 goes with 12. And 5 goes with 10. So we just have a few sample points there for our relation, but in this case you know that all the times in between those points have been met, and all the heights of the candle between those points have also been met. The candle just doesn't jump from 18 centimeters down to 16 centimeters. It will gradually go down to 16 centimeters. So we're going to connect those points, and if we connect them, I find it really hard to draw a straight line with this pen. And you can assume that that data probably starts up, it seems to be going up in a pattern of 2 centimeters every hour, so you can assume that it probably started, because times would start at 0, obviously hours, and they would continue on down till the candle there's nothing left of the candle, I guess. So there's the sketch of the graph. Is the data discrete or continuous? It would be continuous in this case, because all the times and heights between those points used to sketch our graph are possible. So the data is continuous, since all the heights and times between those used to sketch our graph are possible. Okay, looking at, and we already discussed this as well, that the independent variable would be the time, and the dependent variable, so t, and the dependent variable would be the height, or h. And does the graph represent a function? Again, yes, it would. There's no two ordered pairs that have the same first element, and most of the graphs that have a straight line pattern would be considered functions. The only one that wouldn't be a function would be your vertical line. Okay, which brings us to another test for functions, and it's called the vertical line test. So as I just mentioned there before, that a vertical line wouldn't be a function because of course every single point on a vertical line has the exact same x-coordinate. You can use the vertical line then to help you determine if a given graph is a function. And how the vertical line test works is that basically if you can find any place on the graph where you could draw a vertical line and it would hit 2 or more points on that graph, then it's not a function. So if we look at the examples that are here below, we have 4 graphs provided. The first graph is a function because there is no place where you could draw a vertical line that would hit 2 or more points on that relation. So the first one is a function. The second one is not a function because it fails the vertical line test. If you draw a vertical line right here, you've got 2 ordered pairs that have the same x-coordinate of 7, so therefore it fails the vertical line test and is therefore not a function. The next graph has all the ordered pairs are unique x's, which means there's no place on the graph where you could draw a vertical line that would pass through 2 points on the graph. So this one would be a function. And the last one, relation, is not a function because there's a couple of places there that you can draw a vertical line and it would hit 2 or more. This vertical line hits 2 points, this vertical line hits 3 points. So if it hits more than 1 point, if there's any place at all on the graph where it hits more than 1 point, that means there's more than 1 point with the same x-coordinate. So that fails the vertical line test and would not be a function. All right, so these are some examples for us to try now, see if we can use the vertical line test to determine which of the following represent functions. So the first one, there is no place here. If I draw a vertical line anywhere on this graph, every single place I try, it would only pass through the single point. So this one would be a function. Passes the vertical line test. This one here would not be a function, B, because if I draw a vertical line down through 3, nice straight line this time, this would be more than 1 point with the same x-coordinate, so this one fails the vertical line test. therefore not a function. The next one passes the vertical line test. You could draw vertical lines anywhere on that graph and it would never hit more than one spot, so it would be a function. Our next row has 3 graphs, and let's move up so we can get the next one as well. So the next relation is not a function because we can draw a vertical line right here, for example, and that would hit here and here, which means that it fails the vertical line test, therefore not a function. Again, there's lots of places too on the next graph where you could draw a vertical line and it would hit in a couple of places. So if there's one spot that it touches 2 points on the graph, then it's considered not a function. So again, this is a fails the vertical line test, therefore not a function. And the next graph, there doesn't appear to be any spot there where the 2 points are directly on top of each other, which means there's no place that I could draw a vertical line where it would hit 2 points on the graph. So this one appears to pass the vertical line test, so it would be a function. And the next graph, again, there's tons of places I could try to draw a vertical line, but each time it would only go through 1 point on the graph, so this would be a function as well. The next one, it looks like it might not be a function because there are points on top of each other, but you've got to look at it a little bit more closely. This point here, these points here have open circles, so that means they're not actually included. So when you do draw a vertical line through a spot like right here, or right here, you are in fact only going through 1 point because this point with the open circle is not included. So this one would be a function. This one's actually called a step function because it looks like a set of steps. And this one is a vertical line itself in which every single point has the same x-coordinate of 2 in this case, so therefore it definitely fails the vertical line test, therefore not a function. Okay, now there's some questions here at the end on pages 294 and 295 of your text that you can try to see if you understand these concepts. Okay, the next topic in this section goes back to domain and range game, but we're going to introduce a new type of notation for representing the domain and range, and this is called interval notation. So if you look at the data in the table provided here, we have a data that shows time in hours and cumulative rainfall in millimeters. So it started off at time 0, there was no millimeters, and then as the time went on, the cumulative rainfall increased. So if we were to describe the domain for this relation, the domain would be basically describing your independent variable, which would be time. So if you look at the times, even though we have 0, 1, 2, 3, 4 in the table, we know that we're not going to be talking about negative time, but we do know that even though there's whole numbers in the table, all the times between 0 and 1 hour are reached, and so on, and between 2 and 3 and past 4 could also be counted. So if we were to describe the independent variable here, we would basically say that they're all real numbers greater than or equal to 0. Similarly, the range is starting at 0 and increases. Even though there's only certain values shown in the table, we do know that the rainfall doesn't hop from 0 to 1.8 millimeters. It basically will reach all those heights of millimeters in between. Okay, so we would have a description for the range here of all real numbers greater than or equal to 0 as well. If we did it in set notation, we would go back to our basic math statement of x greater than or equal to 0, and then add your fancy stuff on the ends. And of course, x would be would be included there as well. And same thing with your range. Y greater than or equal to 0, then put the fancy stuff on the ends. Y such that y greater than or equal to 0, y is a real number. So another way, those are two ways that we've used already. So if we were to use what we call interval notation, we first need to know how to write with interval notation. So interval notation is only used, it's important to note, it can only be used when the domain and range are made up of continuous data. It's very difficult, or you aren't able to write it when the data is discrete. So it has to be continuous data, and it's written using some brackets, and it indicates the left endpoint and the right endpoint of your values that are used in your domain and range. So the different style of brackets indicates whether or not the endpoints are included or not included. So square brackets mean the endpoint is included, round brackets mean the endpoint is not included. So if we look at some intervals here now, the other thing to note too, if sometimes you'll be talking about values where it just continues to grow higher and higher and higher in value, so then you don't really have a right endpoint. So that would mean you would have to use a symbol for positive infinity, which is extremely large values in the positive direction. And if your values are going smaller and smaller and smaller in the negative direction, then, and there's no endpoint, for example, if you were describing a domain of x less than or equal to 3, that means your right endpoint of the values that are being used is 3, but your left endpoint just goes on and on and on towards the negative values, further and further towards the negative direction. So that would mean that your left endpoint doesn't really exist per se, so you would have to indicate that with the symbol of negative infinity. If you do use infinity as one of your endpoints, then because infinity is not really positive or negative infinity aren't really a particular value, you would use round brackets to indicate that there's no real endpoint as such. Okay, so for the example that we have above, we had that the domain was bigger than or equal to 0. So if you kind of think on a number line, what kind of values are represented, the lowest value is 0, the highest value just keeps going higher and higher and higher. So that would mean our left endpoint would be 0, and our right endpoint would be infinity. And when we write interval notation, we always have it in the order left endpoint, comma, right endpoint. Okay, so the square bracket would be used around the left endpoint of 0 because 0 is a possible value for our time values, and the times keep growing and growing and growing. So really, realistically, we could be checking that rainfall forever. So that would be, infinity would be our right endpoint, and you'd use an open bracket or a round bracket for the right endpoint, because infinity isn't a specific value. And similarly, the range would be described as 0, comma, infinity, but a square bracket around 0 to include 0 as a possible value, and a round bracket around infinity because, again, infinity cannot be reached. So let's try a few examples now just to make sure you understand. And the first example shows a number line, and the domain for the function is shown on the number line below. And if you notice that the lowest x value that gets used is -2, the highest x value that is used is a 3, but 3 is not actually included because of the open circle at the end. You can see there. So our left endpoint in this particular case would be -2. And our right endpoint would be 3. We would have a square bracket around -2 and a round bracket around 3 because 3 is not included. Now we have the word domain in the example here, but sometimes if you just saw the interval like that, you wouldn't know if that was a domain range of values for domain or a range of values for the range. So you would say, oftentimes x belongs to, so then that would indicate that these are possible x values or domain values. The range for a given function is given as y less than or equal to 1. So if you think about that, and sometimes it helps to kind of do a number line. So if you've got 1 right here, and things that are less than 1 would be this way to 1. So there'd be all these values to the left of 1, and including 1 because it says equal to 1. So that would mean our left endpoint is negative infinity, because it keeps going in that direction, and the right endpoint is 1. 1 is included, so there would be a square bracket. Negative infinity always has a round bracket. The next one, and again, you can put, again, we know it's range because it says in the question, but if we were just given that interval and you wanted to make sure that people knew that it was a range, you would put y belongs to in front of that. The domain for a given function, or for a function, is given in set notation as x, the set of all x's, such that the x's are greater than 7 and they're real numbers. So again, if it helps, draw a little number line for yourself. This is 7, and you want everything bigger than 7. So you don't want to include 7, you want it bigger than 7, but you want it bigger than 7 with values on this side of 7. So your left endpoint would be the 7, and your right endpoint would be on forever, so the infinity, open bracket around infinity, and an open bracket around 7, because 7 is not included. And again, if you want to indicate that it is domain, you can put x belongs to in front of it. So if we try the examples down here, the first one, you would have domain, so I'm going to write x belongs to, and my left endpoint is 0, and my right endpoint is 5, and there'd be round bracket around each of those endpoints because open circles at the end indicate that they're not included. This inequality for b is telling you that y is greater than 3 but less than or equal to 10. So basically values in between 3 and 10, but not equal to 3, equal to 10. So you would say y belongs to, so this is obviously a range if the y coordinate is used. 3 is not included, so it'll be open or round bracket. 10 is included, and 10 is the right endpoint, so that would be your square bracket. Now you don't have to draw the number line that I'm drawing there, I'm just trying to help you visualize the left endpoint and the right endpoint. So again, it helps you to visualize it, 2, and you want everything less than 2. So less than 2, not including 2, and less than would be this way, so the left endpoint of that range of values I hope I'm not confusing you using the word range, but those values that are being used are everything less than 2, so the left endpoint would be negative infinity, and the right endpoint would be 2. And then you'd have open brackets again, because infinity never has a closed bracket. I use the word open and round interchangeably, and square and closed interchangeably, because some books say square brackets and some people say closed brackets, but they mean the same thing. And open and round mean the same thing as well. And this one here, the range, so the left endpoint, again, this is a range, so I would say y belongs to. And the left endpoint would be negative infinity, so use your round bracket for that. And the right endpoint would be negative 4, but negative 4 is included, so we'd put a square bracket there. And this one here, when written in this way, you can easily see that the left endpoint is negative 5, and it's not equal to negative 5, so that would be a round bracket, negative 5, comma, 6, and a round bracket there as well. And for f, it would be x is greater than or equal to 0. So again, if it helps you with your number line, here's 0, everything bigger than 0 would be this side of 0, and you're including 0. So in interval notation, that would be x belongs to, close bracket, 0, comma, right endpoint would be infinity, open or round bracket. The next example has x is bigger than or equal to 4, so your left endpoint would be 4 and a square bracket because 4 is included and everything above 4, so on to infinity. And then the last one, your y's would belong to the interval from 0 up to 3, and again there would be square brackets around both of those because equal signs are used with your inequalities, which means the endpoints are included. So we look at example 2. We want to determine the domain and range for each of the functions graphed here. They're asked to do the two new methods we've learned this chapter, set notation and interval notation. So the domain for this one, this graph continues to go out, 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 out. All possible values are used, so that would be x is a real number. And to put that in set notation, you just put your curly brackets, x such that around that. So in interval notation, that would be x belongs to. Again, if there's basically all possible values, that would mean from negative infinity up to infinity. Your range starts, the lowest y that's used there, you can see, is negative 4. And everything above that gets used because there's arrows there to indicate that the graph keeps getting higher. So basically an inequality to represent that would be y greater than or equal to negative 4. And we can have it equal to negative 4 because this point here actually has negative 4 as a coordinate. So then you would put your curly brackets y such that, and y is a real number. To write that in interval notation, your lowest value is your left endpoint, which is negative 4. And it keeps going and going and going higher than that, so that would be infinity would be your right endpoint. So all the values from negative 4 on. And then that would be an open bracket around infinity, and because negative 4 is included, there would be a square bracket around negative 4. Okay, the next example has a graph that starts at negative 3 here on the x-axis and keeps going until positive 3 on the x-axis. So set notation to represent that would be the x's that get used are from negative 3, but not including negative 3, because there's an open hole there. But at 3, the endpoint at 3 is filled in, so that means it can be equal to 3. And you would have, in set notation, your curly bracket, x such that, and this is continuous data here, so it'll be all real numbers. And your interval notation for that domain would be x belongs to negative 3 would be your left endpoint, positive 3 would be your right endpoint. You would include positive 3, the right endpoint, but not negative 3. So round bracket around negative 3, square bracket or closed bracket around 3. For the range, if you look at the y values, now the y value is a little hard to read here for this one. The lowest y value looks like not quite negative 1.5, but let's say negative 1.2, up to about 6, up to 6. So we're going to have to approximate. So y is in between, it's bigger than or equal to negative 1.2 and less than or equal to 6. Now, even though there's an open hole there at the point negative 3, 0, that value for y is used because right here, this point has a y value of 0, and again, another point there has a y value of 0. So the lowest value of y is down here at this height right here, negative round, we said around negative 1.2. And like that open hole there is, even though it's not included there, is included over there. So we basically all values from negative 1.2 up to 6 are used. So then we would have our curly brackets, y such that, and again it's continuous data, so it's all real numbers. in between those values. And in interval notation, interval notation, you would have the lowest value was negative 1.2, and the highest value is 6, and those would both be included, so you'd use square brackets around them. Alright, so the next example has some questions related to domain and range again, where you're given the graph of a function and you're asked to use the graph to determine the range value when the domain value is 2. So the domain value is 2 means the x-coordinate is 2. So if you look on the x-axis and find 2, you basically just look at going up to the graph at an x-coordinate of 2, what's the y-coordinate that goes with that point. So the range value, in this case, that goes with an x of 2 is 5, because that point there has coordinates 2, 5. So when x is 2, the y, or range value, is 5. The next question asks us to use the graph to determine the domain value when the range value is negative 3. So this time we have to look on the y-axis at negative 3, and don't have to go very far for that one, because the actual point on the graph that has a y value of negative 3 is actually on the y-axis. So the domain value for that point is 0, because coordinates of that point that has a range value of negative 3 is 0, negative 3. So you can always, because when we're just looking at the graph here, but we can always check our answers by plugging the values that we were given back into the equation, because we know the equation for the graph that was given to us. So if we know for A that the domain value is 2, algebraically we can find g of 2 by plugging 2 into the equation for x. That gives us 8 minus 3, which is in fact 5. So and when we look at the graph, we pick the right answer. And if g of x, the next one, says that the range value is negative 3, that means you would be solving an equation negative 3 in for the value, and you'll be looking for the x. So then you would have to isolate the 4x by getting rid of this negative 3 on the right-hand side by adding 3 to both sides of the equation. And when you add 3 to the right side of the equation, the negative 3 and positive 3 cancel, so you're left with just 4x. So then negative 3 plus 3 would be 0 equals 4x. And then if you divide both sides by 4 to get the x by itself, you would end up with 0 equals x, which is what we got when we did it by using the graph. Okay, so the next example is same type of thing, just a different equation. And this one has the graph of the function h of x equals negative x plus 2. So you're asked to find the range value when the domain value is negative 2. So the domain value of negative 2 would be on the x-axis of negative 2. You just go up till you hit the graph. There's the point that has an x value of negative 2 on that graph, and the coordinates are negative 2, positive 4. So therefore the range value is positive 4. And then the next equation, the next question asks you to use the graph to determine when the domain value when the range value is negative 1. So you go to the y-axis and find negative 1 on the y-axis, and then match it up with the point that has that y value on the graph. So the point has coordinates 3, negative 1. So that means the domain value when the range value is negative 1 is positive 3. And you can check your answers using the function just like we did above. So for the first one, if we check A, we would be looking for h of negative 2. We want x to be negative 2. So that's going to be the negative of negative 2 plus 2, which is going to be positive 2, plus 2, which is 4. So that was correct from what we had when we looked at the graph. And then if we look at B and check B, we would actually be solving the range value equal to -1. So that would be -1 equals negative x plus 2 is the equation we'd be solving, because we have the y value, we're looking for the x value. So then we want to get the x term by itself, so we want to get rid of that 2. We're going to subtract 2 from both sides of the equation. And when we subtract it from the right hand side, it cancels with the positive 2 that's already there, so we get -3 equals negative x. And then if we divide both sides by -1 to get positive x, we just want to figure out what x is, we end up with 3 equals x, which is the same thing as x equals 3. And this one will be, just go back, y is equal to 4. Okay, that's it for that section. So you can go to your textbook now and try some of the questions on pages 294 to 295 of your textbook. And those questions, 4B, 7, 8, 9, 16, 17, are good practice. And also the function worksheet that we gave out in class is also excellent practice for this material that we've done in this section. And good review of stuff from previous sections as well for the function notation worksheet.